Good afternoon. My name is Kevin Park, and this is Michael Tang, and this is Carlo Ravelli. And today we're going to be discussing the topic of photolithography. And photolithography is basically a process used in microfabrication. So for our experiment we did 2 days ago, we basically had circuit boards and we put film with the desired circuits on it, and then this was exposed to UV light, which allows for the copper not being protected by the film to be exposed, and then this makes it possible. Oh yeah, we have 2 chemicals, and so one is used to develop the circuit, and this makes the copper that's exposed to the UV rays able to be removed, and then the second chemicals is the one we mixed the whole circuit in, and then this removed the copper entirely, and we had to do it for a certain amount of time, around 7 minutes for all the copper to go away. And once the copper is scraped off, the copper not exposed stays, and it reveals the copper circuit, and it's exactly the same as to the design on the film.
All right, so now let's look at the picture analogy for photolithography. So in the first section on the top left, you can see 3 layers. So that might just be some like ground and some dirt and maybe a bit of rocks as well. So that would be representative of spin coating. So when you're setting this up, you would spin coat some silicon to make it a really flat disk. And as you can see, these layers are pretty even and pretty flat. The second picture on the top right, we can see some trees. So these could be representative of a mask. So masking the photoreceptive layer. And then the sun on the next picture in the order could be representing UV light. So the UV light would react with the top layer of the soil, and then the wind could be the developer solution, which removes this layer. Going onwards, the wind could also be the stripping solution, which just blows off the top layer completely. So you're left with that kind of U-shaped piece of dirt. And finally, you have kind of a diagram of like a river meandering, kind of like a cross-section. And this could be, he actually wrote high resistance, so the dirt could be the high resistance layer. And as we know, rivers always take the path of least resistance, in a similar way to how electricity would also take that path. So yeah, and you can see a little transistor here in the bottom right. So yeah, that could be yeah, I think that's just supposed to represent a transistor actually. So yeah, thank you.
So I thought this picture was pretty effective in showing the solubility of the photoresist when it's exposed to light, and showing how like the film shields like some parts of the metal, but the transistor though, like it looks like it was just like hastily put there. Like they could have showed the functions of it. Like if I were to change this, I would like change it to like, I don't know, bridges or something to show the flow of electrical current. Yeah, I think that would have made this drawing better. Yeah, that's.
Questions? Thank you. Just over here, Sarah.
Could you guys talk about positive and negative photoresist as they relate to this drawing and to
I'm just kind of going off a kind of guess with a positive photoresist. So leave the parts where the UV light has shone on, and the negative photoresist would kind of leave an inverse imprint after the developer solution washes everything away.
Okay, and so in this drawing, where's the mask?
So
Or what is the mask?
the trees are the trees and the kind of tree roots are the mask. And so I think this actually shows positive photoresist because is that right?
I mixed up with positive and negative, but forget the words, what's the concept? So here, tell me about where the mask is and where the stuff that's gone.
Yeah.
And your experiment, tell me about where the mask was and where the stuff that was gone.
Okay, so the trees are in the same position as the sediment that's kind of deposited. So it's actually the opposite to what we had in our experiment.
That's right. In your experiment, the part that where the mask was that
Yeah.
was protected from the sunlight is the part that remained.
Mhm.
In this, the part that where the mask is what goes away. And both kinds exist and are used commercially, but it is the opposite of the one that uses.
Okay, sweet. Any more questions? Yes. So this is all. Everything is actually happening on a nanoscale. So this is actually supposed to represent transistors inside a microchip. So so in real life, this would I think it's like 10 nanometers. It's like around that size. So that would be the size of one transistor, and all this is kind of creating one transistor. I don't know the answer to that.
You can make a little tiny mask. What could you maybe tell me about making a little tiny mask?
Do you use light to make the mask? No.
Wouldn't it be like harder to like shape the copper, I guess? Like, but it would be easier if you like did it on the mask though, because you're basically like, because it's not like you're like carving it, right?
Well, actually, when you make the mask, you are carving it, but not with your hands. Usually with an electron beam writer. So, but the question is a really great one. If you can make the mask, why do you need to do this? Why don't you just make the transistor the same way you made the mask? Given that we said you have to carve the mask with electrons, what might you think about that process?
Is it because the copper conducts electricity? No? Okay.
Does it seem like an easy process?
Think about how many you have to put into a chip that's in your cell phone. How many transistors in your chip?
It's like 30 billion.
Yeah, how long does it take for you to draw the number?
Take very long.
Yeah, it would take longer to like shape each copper piece than to shape like each mask, because wouldn't it be like easier to, because the mask is like much easier to make, right? So you could like produce more of it, I guess.
Harder to make. So the mask is really slow to make, And what does hard equate to in this world?
Expensive.
Expensive. So the mask is really expensive to make. So now why would you want to do this process? You make one expensive mask.
Oh, because you can reuse the mask multiple times.
Millions of times. You make one expensive mask, and then you can just shine light through it. One chip, shine light through it. Next iPhone, shine light through it.
Yeah.
So none of us would have a phone if you had to write every circuit with an e-beam writer. That would be way too expensive.
Wait, one question over here.
Since we're talking about the mask and also how to manufacture a pattern, so the question is, what kind of material used to make a mask? Is it copper or some other material?
I think. Do you remember what material it was made of? Do you know?
Well, you didn't use a real mask, so what was your mask? What was your
I think it was a plastic of some sort.
laser printer on transparency? Okay. What's a real mask made out of? Any ideas?
Light sensitive material.
Just metal.
Metal.
Metal with one side of glue.
No, typically not copper. I think people use gold. I think people use titanium. I think the key is to be able to precisely, so the edge has to be sharp. And some metals are like copper, not good.
Yeah, oxidation can actually make the edges uneven. So they use really expensive metals on top of that. A lot of them are concrete because those break easily. They're easy to break with the e-beam.
Yeah, so that's not a There's a huge amount of consideration and restrictions as you already went on. And that's why the mask is so expensive. You're going to repeat it multiple times, one by one, in 1 year, 100% perfect in terms of precision. So